There is a common misconception that just because a problem is hard, it means that every instance of said problem is hard. However, this is not the case, and this observation lies at the heart of my research. I am Alexandra Lassota. I'm an assistant professor in the Combinatorial Optimization group at TU Eindhoven, and my main object of interest are integer programs. In integer programs, we want to find an x such that all these constraints are satisfied. So we want to maximize an objective function C transpose x such that the constraints ax smaller equal b are satisfied, and hence the name, x is an integer. If we just look at the constraints here, we can visualize them as follows, where we see our matrix A, our desired vector x, and the right-hand side b. This problem in all its generality can capture many problems from combinatorial optimization, such as graph problems, string problems, scheduling, bin packing, and more recently it has been applied to machine learning and social choice problems. However, this problem, if solved in all its generality, is NP-hard, which means, assuming that we believe NP is unequal to P, we will have an exponential blow-up in the runtime of any algorithm that solves the most general variant of this problem. But as I said, if we actually look at specific instances, for example, that arise from a specific scheduling problem, we actually will maintain and will have a lot of structure, especially in the constraint matrix, which we then might be able to exploit. And this is exactly my research. I look at these specific structures and I look which ones can we solve, and I design the algorithms to actually solve them. For example, if our constraint matrix is kind of sparse and the column interaction, so columns that are non-zero in the same row, gives us such a tree-like structure, we can actually solve it efficiently. The same holds if we have something like a matching matrix. That is, if for each column we sum up the absolute values of entries, and this is bounded by 2, and even if we then attach a little bit extra here, we can still solve it efficiently. A very famous example are also matrices that have bounded subdeterminants. For example, if they are bounded by -1, 0, and 1, the matrix is totally unimodular, and yet again, we can solve it efficiently. Doing all these efficient algorithms, I also study which applications we can actually solve and in which way. One of my favorite applications that I studied a lot is scheduling. In scheduling, we are given a set of jobs which each have a different running time, here displayed by the height of these blocks. And our goal is to schedule them on machines, so to assign every job to one machine, such that the finishing time of the latest machine is as early as possible. This is called the make-span or the make-span minimization problem. And this is relevant for, of course, processor scheduling, but also scheduling real people in their shifts. And if we change the objective function, for example, we want that the least load on the machine is as large as possible, we can also model Santa Claus. We want to give the least lucky child as many presents as possible. And now solving it using LPs, all we need to do is just squeeze this problem into this form. And of course, this is a very hard thing for many problems to do it. It can take a lot of effort to actually do this modeling part, but once the modeling part is done, we can just rely on the algorithms that we developed a priori. I study special structures of such scheduling. When I want to transform them into integer programs, I solve them exactly, but also oftentimes approximately, because the problem itself is NP-hard, so we cannot hope on efficient algorithms, also not going via special structures of integer programs. I also study different facets of it, which can be fairness. So we do not only want to schedule jobs to machines to minimize the make-span, but also make the actual workers happy with the share they get. Another very common problems of online scheduling. You see a job, you need to assign it before you see the next job, and you basically don't know anything about the whole instance. I also study prediction models, which means we have historical data, so we might kind of know how the instance looked like, but these predictions can be, of course, flawed. Overall, everything I said can be summed up by I study fundamental research in complexity theory? Or how much time do I need to solve this problem? And if you have interest or you feel like I can help you with anything, please feel free to reach out. Thank you.